Molecules leave a boiling liquid to form a vapour. The vapour and liquid have the same temperature. What is the change of the average potential energy and the average random kinetic energy of these molecules when they move away from the vapour? If they have the same temperature, then the kinetic energy is the same. Okay, so the kinetic energy that something has is indicative of the temperature of the molecule. So there's no change to the kinetic energy. So it's either B or D. The fact that they go from a liquid to a vapour means that they increase in distance from each other, and that means that the potential energy increases. So our answer is B. Which of the following is equivalent to a temperature of minus 100 degrees Celsius? Okay, I always remember this by saying 0 Kelvin is equal to minus 273 degrees centigrade. So minus 100 degrees centigrade equals 173 Kelvin. I always just remember that, and that kind of helps me with any conversion that needs to be done. A sample of solid copper is heated beyond its melting point. The graph shows a variation of temperature with time. Now this is it in liquid form. This is it vaporizing. And that's it in gaseous form. During which stages are there an increase in internal energy of the copper? In all three phases there are increased internal energy. Internal energy is the total sum of the random kinetic energy of the molecules plus the potential energy of the molecules. When it's the same temperature as it is on Q, then this stays the same, but potential energy increases. And when it is in P and R, both the potential energy and the kinetic energy increase. So the answer here is 8A. Explain in terms of the energy of its molecules why the temperature of a pure substance does not change during melting. Okay, that's 3 marks. During melting, energy is supplied to the molecules to break bonds. This increases the potential energy between molecules. Therefore, no change in kinetic energy. It's worth putting in here, kinetic energy is proportional to temperature. So if EK is unchanged, then temperature is unchanged. Great. 11B. Oh, so we've got a calculation here that we see quite often in paper 2. 3 ice cubes at a temperature of 0 degrees are dropped into a container of water at a temperature of 22 degrees. The mass of each ice cube is 25 grams and the mass of the water is 330 grams. The ice melts, so the temperature of the water decreases. The thermal capacity of the container is negligible. And we've got some data there. So let's have a think about this. We've got some water, 330 grams of water at 22 degrees. We have 3 ice cubes at 0 degrees, and that is 75 grams. There's going to be a transfer of energy here. The water will lose energy and change temperature. The ice cubes will gain energy, they'll melt, and increase in temperature. So let's think about this. Let's put a temperature scale. This is 22 degrees Celsius, and that's where 330 grams of water is. This is 0 degrees Celsius, and this is where 75 grams of ice are. The ice is going to gain energy and reach a temperature as yet unknown, and the water is going to lose energy and reach a temperature of 22 minus delta T. So, energy gained equals energy lost. So energy gained, well, there's going to be energy into melting the 3 ice cubes, and for that we use the latent heat of fusion. So 0.7, and that's ml. That's the equation for latent heat of fusion, times 3.3 times 10 to the 5. So that's going to be the energy gained to melt the ice cubes. Then that water will increase in temperature by this amount. So mc delta T. And the energy lost on the other side is the energy that the water changes in temperature down to, so it's mc 22 minus delta T. So it's 0.33 times 4.2 times 10 to the 3 times 22 minus delta T. So let's pop some numbers into this. Let's take each side over. So our answer is delta T, which is the final temperature, 3.4 degrees centigrade. You will see other questions that look exactly like this in your paper too, and I'm sure they will come up later on in this paper. This question is about internal energy. Mathilde raises the temperature of water in an electric kettle to boiling point. Once the water is boiling steadily, she measures the change in mass of the kettle and its contents over a period of time. So we're now looking at latent heat of fusion, latent heat of vaporization. And there's some data here. So what we have is initial mass, final mass, time, and power. And we know there's going to be energy that goes into the system that causes the water to boil and float away as a gas. So the energy into the system is going to be used as latent heat of vaporization. And we want to work out what this value here is. We know how much power is into the system over a length of time. So the energy into the system is power times time. And the change in mass times L, we know what the change in mass is. So we simply put the numbers in. 2.5 times 10 to the 3 times 300 seconds equals the change in mass, which is 0.3, that's 1.880 minus 1.580 times L. L is equal to, let's pop this into our calculator, 2.5, oh, we probably could have done that in our heads actually, couldn't we? Times 10 to the 6 joules. So let's call that 2.5 megajoules per kilogram. Forgot to put the kilogram up there. Joules per kilogram. There we are. Outline why your answer to B1 is an overestimate of the specific latent heat of water. Well, in this question up here, we are assuming that all the energy from the kettle, from the heating elements of the kettle, are used to boil the water. In fact, some heat energy will be lost to the surroundings. Therefore, E is smaller, mass is the same, so the latent heat of vaporization will be smaller in real life too. A fixed mass of water is heated by an electric heater of unknown power P. The following quantities are measured: mass of water, increase in water temperature, and time for which the water is heated. In order to calculate P, the specific heat capacity of the water is required. What is also required? Well, power times time equals mc delta T. If we want to find out what P is, we need to know the mass of the water, or the change in mass of the water, specific heat capacity, which is given in the question, change in temperature, and the time over which. So we are looking at all three. D. A block of iron of mass 10 kilograms and temperature 10 degrees is brought into contact with a block of iron of mass 20 kilograms and a temperature of 70 degrees. No energy transfer takes place except between the two blocks. What will be the final temperature of both blocks? So we have a smaller mass, which is 10 degrees. We have a larger mass, which is 70 degrees. And this is 2 times the mass of mass 1. The change in temperature between these two objects is 60 degrees Celsius. We know that the larger mass is going to decrease in temperature and the smaller mass is going to increase in temperature. Given that the smaller mass has a smaller mass, we expect that to increase in temperature by double the amount than the larger mass does. So if we say that 60 degrees is the total temperature, we expect the larger mass to decrease by 20 degrees and the smaller mass to increase by 40 degrees Celsius, which leaves us with an equilibrium temperature of 50. The specific latent heat is the energy required to change the phase of 1 kilogram of a substance. Getting there. We do want to include 1 kilogram. A substance at a constant temperature. Getting there. We do want to include constant temperature. Don't really care about liquid because it hasn't said whether it's fusion or vaporization. So the answer is 1 kilogram of a substance at a constant temperature. 1. Define the specific latent heat of fusion of a substance. Okay, so let's write that down here. The specific latent heat of fusion is equal to the energy absorbed or released, depends on what direction we're going in, when 1 kilogram of a substance freezes at a constant temperature. It's really important to say at a constant temperature. That is part of the definition. And you could have put freezes or melts. And what that does is it accounts for this idea as well. Okay. Part 2. Explain in terms of the molecular model of matter the relative magnitudes of specific latent heat of vaporization of water and specific latent heat of fusion of water. Okay, the latent heat of vaporization is much, much greater than the specific latent heat of fusion. So it takes more energy to turn it from a liquid to a gas than it does to turn it from a solid to a liquid. And why is that? Well, that is because here, on a liquid to a gas, we're actually breaking the bonds between molecules. And in here, we're simply weakening the bonds. So when we go from a solid to a liquid, the bonds still exist, but they're weakened. When we go from a liquid to a gas, the bonds completely break between the molecules and they move apart. And that requires more energy than it does to weaken the bonds. There's our explanation. A piece of ice is placed into a beaker of water and it melts completely. The following data are available. Determine the final temperature of the water. Okay, well, this is exactly the same sort of question as we had earlier. We've got a water, and the initial temperature of the water is 80 degrees Celsius. It is 0.25 kg, and we put some ice in there that has an initial temperature of 0 degrees Celsius, and it is 0.02 kilograms. So the water is going to lose energy, and the ice is going to melt and gain energy. And let's do our temperature scale. The water starts at 80, and it will go down to a certain temperature. We don't know what that is yet. The ice starts at 0 degrees centigrade and will increase by delta T. That means that the water will decrease by 80 minus delta T. So taking the fact that the water will lose energy, it will lose this amount of energy, MC 80 minus delta T. That's what the water will do. And the ice, first of all, will melt, so it will use this amount of energy to melt. And then it will increase in temperature by that amount. So let's put the numbers in. The mass of the water is 0.25 times the specific heat capacity of water times 80 minus delta T. The mass of ice cubes, first of all, melt using the specific latent heat of fusion. Then it will increase in temperature so let's see if we can simplify this equation by popping some numbers in. So the temperature is 68.3 degrees Celsius. Is that correct to the right number of decimal places and significant figures? Yeah, I think we can get away with that. That looks good. Now, to state two assumptions that you have made to answer this question. Well, it's similar to the assumptions we've made before. The first assumption is that no energy is lost to surroundings. E.g. the beaker. And the second assumption, a little bit more complicated, is that the water does not evaporate, because when the water evaporates, it loses energy, but it also loses mass. It loses energy, but it also loses mass. So don't forget about evaporation. Two objects are in thermal contact, initially at different temperatures. Which of the following determines the transfer of thermal energy between the objects? Well, the rate of transfer, it makes a difference, but the transfer of thermal energy just tells us what direction it goes, and the only thing that matters here on that is the temperature. D. Which of the following can be determined for a solid substance, which are equal to the internal energy? Right, so the internal energy is equal to the total kinetic energy and the total potential energy. So we're looking at 1 and 2. Sorry, not 1 and 2. 2 and 3. D. For a black body at absolute temperature T, the power emitted per unit area is P. What is the power emitted per unit area when the temperature is decreased to the half of T? If you go to your data booklet and you look at the power equations there, you will find that the power is proportional to the absolute temperature to the power of 4th. So T1 is equal to T. T2 is equal to a half of T1. Let's pop P2 is proportional to a half of T1 to the power of 4th. Now a half to the power of a 4th is equal to 1/16. So P2 is proportional to 1/16 T1 to the 4th. So our power of P2 is going to be 1/16 of the power of P1. The answer is B. Increasing the temperature of a black body will have the effect on its emission spectrum. Let's just remind ourselves about the black body power wavelength graph. They look like this. And these are temperatures, aren't they? T1, T2, and T2 is greater than T1. That should be in your common graphs section. You need to plot this in your common graphs section of your revision note template. You can see that with a higher temperature, which is what we're saying in question 10, the wavelength decreases. And you can see that the total power, which is on this axis here, increases. The answer is A. Question 15. In an experiment to determine the specific latent heat of fusion of ice, so we want to find out what LF is, an ice cube is dropped into water that is contained in a well-insulated calorimeter of negligible specific heat capacity. The following data are available. And we've got the mass of the ice cube water, the temperature change, and various other things. A. Using the data, estimate the specific latent heat of fusion of ice. So we want to find out what LV is. To approach this question, we need to think about what's happening in terms of energy. So we have our calorimeter here, and the question makes it very clear that we can ignore anything to do with the calorimeter heating up or losing energy and so on. So we're only concerned with the water in the ice. So we've got water. It's 350 grams of it, and it's initially at 18 degrees Celsius. We drop the ice cube in, and the water goes to 12 degrees Celsius. What that tells me is that the water is experiencing an energy loss. It's losing heat energy, and that heat energy is being transferred to the ice cube. And the heat energy that's being transferred to the ice cube must be equal to the energy lost by the water due to the conservation of energy. So we've got an equation here of energy loss equals energy gain. And this is energy lost by the water, energy gain by the ice cube. Now what energy is lost by the water? Well, it's losing heat energy. And the equation for that is mc delta T. So the amount of heat energy it's losing is 0.35 times 4200 times the change in temperature, and it's losing 6 degrees. Let's look at the energy gained by the ice cube now. Well, the energy gained by the ice cube has to take into account the fact that it has to melt first. So we look at the specific latent heat there. I put V there, sorry, it should be F. And then, once it's melted, it has to raise in temperature from 0 up to 12. So these two equations here represent the equation of energy gain of the ice cube. So let's pop our numbers in. 0.025 times 4200 times 12. And when we pop all the numbers in and rearrange for LF, what we get is LF is equal to 3.02 times 10 to the 5 joules per kilogram. That's 4 marks. I love it when we get a question in thermal physics that offers 4 marks because they tend to follow exactly the same format. What's losing energy, what's gaining energy, make a little equation and rearrange it. It's a really great way to get 4 marks. Let's go on to question B. The experiment is repeated using the same mass of crushed ice. So the mass stays the same and crushed ice. What's the difference between crushed ice and an ice cube? Well, the surface area of crushed ice is greater than the surface area of a cube. That's the only thing that's different. Suggest the effect, if any, of crushing the ice on the final temperature of the water. Well, we saw earlier that the equation was MLF plus T. And this was the ice cube. At no stage does area come into this equation. Okay, so what that means is that area or surface area doesn't have any effect on the final temperature of the water. So there is no effect on the final temperature. As it is independent of surface area. And I think the mark scheme says the energies are the same, but we've kind of shown that with that equation. B2, the time it takes to reach the final temperature. Okay, well, if you increase the surface area, you increase the rate of melting. Okay, if you increase the rate of melting, then you decrease the time it takes. So therefore, the time taken to melt and reach final temperature will decrease. Question 16. Each side of the ice cube is 0.75 metres in length. So we've got an ice cube like this. This is obviously a follow-on from another question, by the way, but we don't need to know what the rest of it is. We can just get on with this. Each side of the cube is 0.75 metres in length. Okay? The initial temperature of the ice cube is minus 20 degrees. 1. Determine the energy required to melt all of the ice from minus 20 degrees to water at a temperature of 0 degrees Celsius. And we have this data here. We know that the energy is going to include 2 things. It's going to include the energy required to melt it from ice to water. That's the specific latent energy of fusion. And it's going to involve the energy required to take the temperature of the water from minus 20 all the way up to 0. And to do that, we quite clearly need mass, but we haven't got mass at the moment. What we have got, however, is volume, because the volume of a cube is... So the volume is 0.422 metres cubed. And we also have density. We know that density equals mass over volume, so we can find mass by multiplying density by volume. So we've got 920 times 0.422 gives us a mass of 388.125 kilograms. We'll just keep it that accurate at the moment and we'll deal with it later. Now we can pop into this equation. We can say, okay, the energy required to melt the ice cube is 388.125 times the specific latent heat of fusion of ice, which is 330 kilojoules, 1, 2, 3, plus the energy required to bring it from minus 20 all the way up to 0 degrees, which is 20. Let's see, that's energy. Let's pop all our numbers into there, and that gives us an energy of 1.4 times 10 to the 8 joules. And if you wanted to bring it something a bit more palatable, it'd be 1.4 times 10 to the 5 kilojoules. And the only reason I would put it into kilojoules is because these were in kilojoules. It just makes it a bit nicer. Again, 4 marks. That's a lot of marks for something that's relatively simple. B. Outline the difference between the molecular structure of a solid and a liquid. Well, a solid looks like this. I'm not going to take ages doing this. And a liquid looks like this. What's the difference? Well, solid, liquid, both closely packed. So that's not a difference. Oh, a solid has a fixed structure. And a liquid, they move easily around each other, don't they? They can easily move. In a solid, you'd also have strong bonds of attraction. So these molecules are being kept together very strongly, whereas in a liquid, it's less strong. That's the best way to write it. Bonds of attraction. That means that if you were to put a little bit of energy into this, those bonds could be broken, and it could quite easily turn into a gas. Whereas in solid, you need a lot of energy to go into it before those bonds would be broken. So either of those two would make a fine answer to get your 1 mark from the examiner. Question 17. An ice sample is moved to a laboratory for analysis. The temperature of the sample is minus 20 degrees Celsius. 1. State what is meant by thermal radiation. Well, radiation is something that's been given out, that's been emitted, and thermal is infrared. So it's the emission of infrared, or we can put in electromagnetic here, radiation. 2. Discuss how the frequency of the radiation emitted by a black body can be used to estimate the temperature of the body. Okay, well, frequency of radiation can be used to determine the wavelength of radiation. And we can put in C equals F lambda there to help that conversion. And then the second point is Wien's displacement law is lambda peak times T equals 2.90 times 10 to the minus 3. So once lambda peak is known of the black body, Wien's law can be used. My writing's terrible today, I'm so sorry. Let me just write that bit again. Can be used to find temperature. 2 marks. Calculate the peak wavelength and the intensity of radiation emitted by the ice sample. No problem. So we've just used the equation we've just spoken about. Lambda peak, T, Three, calculate the peak wavelength and the intensity of the radiation emitted by the ice sample. Well, no problem. We'll use the relationship we've just talked about. The only thing we have to do here is change our temperature from minus 20 degrees Celsius to Kelvin, and that will be 253 Kelvin, because don't forget that 0 degrees Celsius is equivalent to 273 Kelvin. So minus 20 degrees Celsius is 253. Therefore, lambda peak equals 2.90 times 10 to the minus 3 divided by 253, which gives us a wavelength of 1.1 times 10 to the minus 5 meters. 4. Derive the units of intensity in terms of fundamental SI units. Okay, well, intensity is the amount of energy per unit time across a unit area, or watts per metre squared. Metre squared is an SI fundamental unit, but watts is not. Okay, so we need to find watts in terms of fundamental SI units. Well, watts is the unit of power, which is energy over time. And energy over time is the equivalent of work done, which is force times distance divided by time. And force is equal to MA over time. So power can equally be expressed as MAD over T, mad over time. Why am I doing this? Well, I'm trying to find the fundamental units here. Well, we know that the unit of mass is kilograms. That's a fundamental SI unit. We know that the units of acceleration are meters per second squared. They're both fundamental. And distance is meters. That's a fundamental as well. Over time, again, fundamental. So let's break that down. We've got kgm squared s to the minus 2, s to the minus 3, because we're taking that s up. So the units of watts in fundamental units is kgm squared s to the minus 3. So let's take it here and put it into fundamental units. kg m squared s to the minus 3 m to the minus 2. These m's cancel out, so our final units are kg s to the minus 3. That is the units of intensity in terms of fundamental SI units.